For over a century, physics has treated time as a smooth, continuous river. But if we look at the universe at the smallest possible scales, that continuous fabric shatters. Reality doesn't flow, it updates, frame by frame, in discrete, quantifiable steps. This discrete architecture forms the basis of the infinite fractal descent framework. In this model, the universe operates as a gravitonic universal quantum computer, a processing engine where everything observed is the result of a universal recursive algorithm. The clock rate of this processor is anchored to the most stable oscillatory processes in existence, specifically the quantum resonances stabilizing the cosmic microwave background. If reality is updated tick by tick, physical matter is not an inherent property of stuff. Instead, mass is a measure of computational resistance, the informational cost of rendering a structure within the universal substrate. The fundamental unit of this computational step is the universal tick, or omega time. Operating at the Planck frequency, it represents the absolute smallest increment of time. This tick acts as a constant digital oscillation. It provides the background rhythm required to maintain structural coherence across all universal wave patterns. This chart traces the normalized universal scale. The far left begins at the Planck epoch, following the Big Bang. At exactly omega t equals 1, we hit the first tick, ending the Planck epoch. This is the instant the universe became algorithmically measurable. As biological internal rhythms synchronize with these universal omega cycles, they recycle entropy across deeper fractal scales to maintain their structural coherence. Inert systems allow these ticks to pass with minimal resistance. But when complex structures form, they act as interruptions in the flow, forcing the substrate to dedicate more iterations to their existence. Simple matter lets the universal algorithm glide by, but complex geometry tangles the code. These structures act as topological knots, stable excitations known as hopfions. When the universal recursive algorithm encounters one of these knots, it forces a localized concentration of operations. We call this metric iteration density. This density is governed by the minimum description length principle. It states that the more recursive patterns a system contains, the more its energy density and its effective mass is localized into a smaller volume. This generates algorithmic mass. It is the physical weight of the code required to geometrically encode a structure. Inert structures like monatomic gases and linear polymers show a negligible mass multiplier, possessing very little algorithmic mass. But an information-bearing molecule like the DNA helix requires an exponential leap in computational work. Its multiplier reaches 28.6 times the baseline mass. In this informational regime, mass is not an inherent property of stuff, but an emergent state of coherence and informational cost. Maintaining this coherence is a constant struggle. Complex systems must continuously fight against external entropic dissipation that seeks to erase their structural data. The survival of a structure is determined by its fractal scaling factor. This is a ratio weighing the internal algorithmic work against the external dissipation of the environment. When this factor reaches the threshold of unity, the system's internal work exceeds the entropic leakage. This allows the system to capture the universal tick, achieving a state of localized thermodynamic efficiency. During this transition, the system passes through what universal processors call a promotion gate. To clear these gates, biological structures utilize a golden traversal, a navigation framework based on the golden ratio. By packing information and energy at this specific mathematical proportion, systems reach the efficiency required to sustain life. This transition marks the exact boundary where inert chemistry becomes a self-sustaining architectural engine. However, high iteration density creates a physical problem. When intense complexity is trapped inside a low-density environment, it creates a localized pressure. This divergence generates topological tension, a pressure pushing outward against the boundaries of the system. Polymer networks resolve this by eliminating small pores to protect their structural integrity. They compact and fold to withstand the strain. We see the most observable biological evidence of this tension in DNA supercoiling. The algorithmic mass forces the strand into writhing phases. This mechanical strain is a direct physical consequence of the informational density packed within the helix. If we recontextualize DNA replication through the lens of IFD physics, the process of rolling circle synthesis takes on a different meaning. The buildup of conformational strain and tension actually eases the barriers to strand separation. The tension itself acts as the mechanical driver for the replication process. By bifurcating fractally, by making a copy, the system explicitly halves the topological tension per unit volume. DNA replication is a thermodynamic safety valve, a mechanism for dissipative adaptation that prevents the molecule from being crushed by its own algorithmic weight. The resolution of this critical topological tension generates a selective attractive force, algorithmic gravity. Unlike Newtonian gravity, algorithmic gravity is a selective algorithmic vacuum governed by a resonance filter. This resonance filter dictates that the template will only pull in building blocks that vibrate at its exact cadence. This process is described by the Kuramoto model for phase locking among coupled oscillators. When the coupling between the template and the environment exceeds a critical threshold, the building blocks are forced to vibrate in unison. This synchronization is what creates the sequence specificity of DNA and RNA. Only molecules that align with the cadence of the template can overcome the system's stability guards. Molecular assembly is simply the inevitable synchronization of fundamental quantal frequencies, a temporal alignment forged entirely by geometry and resonance. The final key is Jeremy England's formula for dissipation-driven adaptation. Systems driven by external energy restructure themselves to absorb and dissipate it more efficiently. Self-replication is the most efficient method for increasing that dissipation over time. Life is not a biological miracle, but an inevitable outcome of the second law of thermodynamics when applied to a discrete, recursive universe. Life distributes algorithmic mass into deeper fractal scales. It is matter's transformation from an inert substance into an active participant in the universe.